as 1 plus n times x plus n into n minus 1 by 2 factorial times x to the power 2 plus up to n into n minus 1 into n minus 2 by 3 factorial multiplied x to the power 3 plus so on. Yes. Okay. And just as an example, if we have a form where we have a situation where 1 plus 2 to the power 3 is to be opened, so what we can do is we can open it like this: 1 plus 3 dot 2 plus 3 into 3 minus 1 by 2 factorial dot x square, which is 2 to the power 2, and then we have 3 into 3 minus 1 into 3 minus 2 by 3 factorial and 2 to the power 3. Yes, and we stop here and we don't expand further. So this will be 1 plus 6 plus 3 into 2 dot 4 by 2 dot 1 plus 3 dot 2 dot 1 by 3 dot 2 dot 1 dot 8, or simply 3 dot 2 dot 1 dot 8. Yes, and 3 dot 2 dot 1 and so on. 1 plus 6 plus 12, because 2 cancels out and then 2 cancels out again, and also 3 cancels out, so we're left with 8 and so on, and this gives us about 27 for this much of the opening. So this is how we proceed with the binomial series, and for theorem we have a slightly different structure which we will explain just now. Binomial theorem, and the general form says a plus b to the power n is equal to summation r is equal to 0 up to n combination r, a to the power n minus r and b to the power r. So this is the general form. Okay, so if we have a form which says 1 plus 2 raised to the power 3, and if you're supposed to open it up with the binomial theorem, so the structure would be okay, factorial by n factorial by n minus r factorial. So basically in rough work, n combination r is equal to n factorial by n minus r factorial. Yes, this is important to write here. So we use this form 3 factorial by 3 minus 0 factorial 0 factorial 1 to the power 3 and 2 to the power 0 plus 3 factorial by 3 minus 1 factorial 1 factorial 1 to the power 3 minus 1 this time, 1 to the power 2 and 2 to the power 1. Yes, and we go further. 3 factorial by 3 minus 2 factorial 2 factorial a to the power or 1 to the power 1 to the power 1 and 2 to the power 2 this time. Okay, and there's one more opening which says 3 factorial by 3 minus 3 factorial 3 factorial 1 to the power 3 and 1 to the power 0 and 2 to the power 3. Yes, so this is the form, and now 3 factorial is 3.2.1 in the first term, and dot 1.2 to the power 0 is 1 as well. In the denominator we have 3 minus 0, which means 0. 3 minus 0, which means 3 factorial, so 3.2.1, and 0 factorial is 1, plus in the second term we have 3.2.1.1.2. Yes, by 3 minus 1, which is 2 factorial, which means 2.1, and 1 factorial is 1, plus then 3.2.1 here, 3 factorial dot 1 to the power 1 and 2 to the power 2, which is 4 now, and in the denominator we have 3 minus 2, 1 factorial, which is 1, and then 2 factorial, which is 2.1. Okay, and plus last term 3.2.1.1 to the power 0 is 1 and 2 to the power 3 is 8, divided by 3 minus 3 0 factorial, which is 1 1, and 3 factorial is 3.2.1. okay, so this is the opening in numeric form, and now we go for the solution. 3.2 is cancelled out by 3.2 here, 2 is cancelled out by 2 here, and 2 is cancelled out by 2 here. Once again 3.2 is cancelled out by 3.2 here. So what we're left with in the first term is 1 by 1 plus 3.2 in the second term plus 3.4 in the third term plus 8 in the fourth term. So yeah, 1.1 is 1, so 1 plus 6 plus 12 plus 8, which gives us 27 once again. So this is the solution using the binomial theorem. We resume with the trigonometric identities. Interesting topic. Trigonometric identities. So when we are working with them, we have a summation or a positive or negative summation, like alpha plus beta or alpha minus beta in the angle. So the first one says sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. The second one says sine alpha minus beta is sine alpha cos beta minus cos alpha sine beta. Okay, the third one says cos alpha plus beta, which is cos alpha cos beta minus sine alpha sine beta. The fourth one is cos alpha minus beta. Okay, basically any one of these can be needed anywhere in trigonometry, so having them in mind is important. So cos alpha cos beta plus sin alpha sin beta. Okay, and now we have this form for tangent, which says tangent alpha plus beta is equal to tangent alpha plus tangent beta by 1 minus tangent alpha tangent beta. Tangent alpha is the slope in the Cartesian plane for lines, but we will look at that later. Tangent alpha minus beta is tangent alpha minus tangent beta by 1 plus tangent alpha tangent beta. Okay, so this is not difficult to visualize. And this can also be put to use. And I will tell you how. We resume and look further into the trigonometric identities. For example, we take the first one, which is here, and the second one, the third one, the fourth one, the fifth one, and the sixth one. Okay, so we take the first one uh, and we do something like this: sine theta plus theta. Yes, both alpha and beta are the same. So this gives us sine theta cos theta plus cos theta sine theta from the basic form. So sine 2 theta becomes 2 sine theta cos theta. Yes, so this is important in substitutions. And if you go for 2, which is sine theta minus theta, it gives us sine theta cos theta minus cos theta sine theta. Okay, this says what? This says sine of 0 is equal to 0. The third one, cos of theta plus theta is equal to cos theta minus sine theta, which is cos 2 theta equal to cos square theta minus sine square theta. Yes, if we dig further, so we look into the fourth one, which is cos theta minus theta. It says cos theta plus sine theta sine theta. It says cos of 0 is equal to cos square theta plus sine square theta, which means 1 is equal to cos square theta plus sine square theta, or 1 minus cos square theta is equal to sine square theta, and sine theta can be equal to 1 minus cos square theta 1 minus cos square theta under the root. This is the form for the fourth identity, and we will look into the fifth and sixth as well. So the fifth one says tangent of theta plus theta is equal to tangent theta plus tangent theta by 1 minus tangent theta tangent theta. So tangent to theta is equal to 2 tangent theta by 1 minus tangent square theta. Yes, and there are many different iterations, and the sixth one is tangent theta minus theta is equal to tangent theta minus tangent theta by 1 plus tangent theta tangent theta. So tangent of 0 is equal to 0 by 1 plus tangent square theta. Sin 0 1 cos 0, sin 0 0 cos 0 1, so 0 by 1 would be 0, and 0 by this would also be 0. So the sixth one doesn't seem to be very significant, but it is worth a try. So I am somewhat tempted to include numerical analysis fundamentals and the Newton-Raphson method,